So hello everyone, my name is SJ. I'm working as a kernel engineer at Meta and currently maintaining DAMON subsystem of Linux kernel, which is for efficient memory access monitoring and access-aware memory management optimizations. So I will start from giving you a very short user story about giving you a very brief idea about what I will talk today, and then I will describe a little bit details about what is the observer effect in memory management and how DAMON, which is the topic of this talk, overcomes the observer effect, and then introduce a few DAMON use cases in real world, and then letting you know how you can get started at using DAMON and development of DAMON, and finally we will have a brief Q&A. So let's start from a user story. So once upon a time, not that very long ago, but in 2021, in a cloud provider named AWS, far, far away, there was an awesome team that found a very interesting findings. That is, they found that the real memory usage of given workload would be not always very same to or more than the given amount of the memory for given virtual machines. And therefore, they made a very brilliant idea that is maybe they can dynamically adjust the size of the memory of the given virtual machine to just fit only the real memory requirements of the given workload. Why do that? Because the service provider can get benefit from having higher physical resource efficiency. That is, they can serve more workload with given finite amount of memory, and also with that they can have some rooms to cut user price so that they can attract more users. And from perspective of users, they will still have the no degradation of the performance, the same performance, but having less cost because the service provider could give them the price cut. And while doing this work, the team has found that it is not very simple as they have imagined at the beginning, especially at knowing the real memory requirements of the given workload. That is a very simple way to think about how many memory the given workload would need. It would be accounting the allocated memory, but that's not really same to the real memory requirement or the performance critical amount of the memory of the given workload. Actually, as you can show on the bottom of this slide, you can show the memory footprint distributions of given workload using DAMON user space tool, like given comment. In the example, it is showing the 50th percentile of the working set size of the given workload was only 15 megabytes, but the residential set size of the workload was about 100 megabytes. And while doing this, the team has found that the major challenge is the overhead and the accuracy. As they want to achieve higher accuracy, the overhead also increased and vice versa. And at the time, which was just before the Linux 5.15, and there was no good solution seemed available at that time. And at that time, in Dresden, Germany, a kernel programmer, who is I, was developed a new kernel feature and was looking for a user of the new features. And the feature was advertised as something that can provide something that the service team was looking for, that is finding the real memory usage of a given workload in a very efficient way. And they somehow eventually met and co-developed the service with the kernel feature, the memory autoscaling feature service with the kernel feature. And they lived happily ever after. So as a result of the co-development of the service was able to be successfully launched in name of Amazon Aura Serverless v2 and still successfully being serviced. And the kernel feature that the guy from Dresden was developing has been also merged into Linux 5.15 in name of DAMON subsystem. And DAMON is now continuing its revolution with more new features and more new users. So that was the very simple and happy story about how the memory autoscaling service was developed and what kind of problems they have found. Now let's see in more details about what was the problems namely the object effect in memory management, the service team was finding and struggling about, and how the kernel feature that developed by the guy who was living in Dresden has developed to overcome that, and then the use case and getting started and Q&A. So first of all, the object effect in the memory management. We can fundamentally say that the goal of the modern computers is the processing of the data, and the memory is a medium for storing and loading the data to process. And one consistent trend that we are seeing from the history of the computer science and the industry is that the size of the data is always exploding. And that is, otherwise, why would we need the machines at all? We can just use the machines that already invented, or just don't need the machines at all. And actually, at the beginning of the invention of the computer, in case of Turing machine idea, there was a good idea that the machine would have an infinite amount of memory. But the limitation of the physics is saying that it is not that easy. That is, because of the limitation of the physics, which means that the energy is mc squared, which here m means the mass of electron on modern computer, because the fundamentally speaking, what the computer is doing, moving electrons here and there, and the speed of processor is almost always faster than the speed of memory access, and the cost of the physical memory is usually proportional to the access speed and the capacity of the memory. And we have a solution for this in terms of the hardware. That is, we are now constructing the memory system of modern computer in a hierarchical way. That is, we have multiple memory devices of different types, of different characteristics. That is, we have a small but faster and expensive memory device, and slower but larger and less expensive memory devices. And therefore, we can consist the memory system of the computer to have the fastest and smallest memory device on the uppermost layer, which is the nearest to the processor, and putting or placing the more frequently accessed or hot data on the upper layer of memory device, so that the more frequently accessed data can be accessed more quickly. However, of course, the hardware cannot save the world alone. It needs some help from software, because hardware cannot deal with many too complicated and large-scale use cases. And therefore, we have the software that optimizes the hierarchical memory management. The goal is very simple. So we just want to keep hottest memory or data on the uppermost layer of the hierarchical memory. And how we can do that? We can do that by evicting the cold data to lower layer in name of the memory reclamation or demotion in terms of tiered memory management. And also we can migrate hot data to upper layer in name of NUMA balancing or promotion in terms of the tiered memory management. And the evictions and migrations are also very interesting topics and very complicated and important ones, which is usually made with a magic of the mappings. However, that's not the scope of this talk. Rather than that, this talk will focus on how we can find the cold and hot data. So to say about how we can find hot and cold data, what is the data accesses? We can define the data accesses as a microscope event on space and time of the memory. And that can be simply visualized as a space-time access event map, like showing on this slide. That is, x-axis is showing the time, and y-axis represents the address space, and then we can show some kind of event coming up and goes away on the space and time. And what would be the ideal way or ideal research of the data access monitoring? It would be ideal if we can have very precise monitoring and very complete monitoring in lightweight way. And very simple idea to do this would be just recording every memory access whenever it is made. However, the bad reality or real harsh reality is that the observable effect is inevitable in this way because fundamentally speaking, what we are saying about with the idea is that we want to add monitoring purpose memory accesses and assignment of the memory for that. For each of the memory access, that is, we are adding a work for something that we want to monitor. And therefore, a kind of observable effect is inevitable, as also Paul McKinney has mentioned on his book, saying any data within the system representing state in the real world outside of the system is always and forever outdated. So we need to deal with this, and good reality is that we can always negotiate. That is, we don't really need to know every details in complete history, but for just practical memory management, we can deal with only a high-level view. And therefore, Linux kernel is using not ideal, but practical mechanisms of data access monitoring that I say that we can categorize in two ways. The first category is some of the access monitoring mechanisms that developed and optimized based on what memory management actions we want to make. That is, for memory reclamation, we have developed and optimized the kind of pseudo-LLU mechanisms for that to find cold pages. And also for NUMA balancing like mechanisms, we have developed the artificial and periodic window-based page fault mechanisms to find hot pages. And these kind of mechanisms are very optimized and also time-tested, and therefore just works with the default kernels. However, those are also not very observable but obscure, and sometimes some of the details are based on some heuristics that not very easy to be applied to every case, and also not very easy to extend for general use cases. And there came the second approaches that developed based on the observability first and then later extended for general memory management, which is namely DAMON, the topic of this talk. So how DAMON handles the observable effect? To say that, let's first define what is the goal and the challenges of doing that for using DAMON. So the goal of the DAMON is that we already described what would be the data access patterns, the event on space-time of the memory. So the goal of DAMON is to have the space-time access event map visualization or something that practically same amount of information with that. And what would be the challenge? That is the overhead. So for generating each snapshot of the map, we have the time overhead that proportional to the size of the memory to monitor. And for saving the entire access event map on somewhere, we have the space overhead that proportional to memory size multiplied by the total monitoring time. And this is really bad because the size of the memory to monitor and the total time to keep the monitoring can be arbitrarily huge depending on use case. That is, it is unscalable. That is, some mechanisms could work on computer systems having 1 terabyte memory, but might not work that well on 1 petabyte memory systems. To overcome these problems, DAMON has a few mechanisms. The first one is called region-based sampling. The region is a concept of DAMON that defined as a contiguous area in the space-time of the access event map. That is, it is a collection of the adjacent elements in the time-space access map that having similar access pattern or similar access frequency. And by this definition, what it means is that if we can check access to any of the entity inside a given region, then we don't need to check the access of other elements of the region. Like we can say that this page has access because we have seen the access to a page or cache line in the page. So we can start from defining the region with fixed granularity of space and time, and very simple Boolean access frequency, whether the region has access or not. And by utilizing this, we can simply just split the space-time access event map with fixed granularity time interval, which we call sampling interval, and also split the space with a fixed granularity of size called region size. And then we can check for each of the cells whether the cell representing the given region was accessed or not, at least once or not. By using this, the time overhead and the space overhead are reduced by the factor of the space granularity and time granularity, respectively. That is, we can effectively reduce the overhead, and also the amount of the reduction can be controllable by controlling the space granularity and the time granularity. It is a big improvement, but still the overhead are ruled by the memory size and monitoring time, which can be arbitrarily high. And we can very simply improve this further by increasing the level of the access frequency that we will monitor. That is, we can aggregate multiple access checks into one result of the region. That is, we can accumulate the access check result or positive result per region by using a per region counter that counting the positive result of the access check. For example, we can define one more time interval called aggregation interval, and we do the sampling interval-based access check every time, but count the positive result of the access check on the per region counter like this. And for each of the aggregation interval, we reset the per region counter and then keep going on. By doing this, users can read the rough monitoring results of each region per aggregation interval by reading this counter for once per aggregation interval just before the counters are being reset. Then the resulting visualization would look like this. So by using this approach, we further reduce the space overhead by factor of the n. Nevertheless, still the overhead is still ruled by the memory size and the total monitoring time. And therefore, we further implement the second mechanism called self-tuned region space or adaptive regions adjustment. So from the last research of the visualization, we can find some of the wasteful inefficiency. That is, there are adjacent regions having similar hardness. Those are not really needed, right? And also, this kind of fixed granularity is restricting the ability to monitor fine-grained space of the access pattern. And therefore, we have implemented a very simple but effective mechanism that is, we repeatedly find if the adjacent regions are having similar access frequency or not, and if so, because those are just wasteful, we merge those into one region. And also, because there could be some dynamic access patterns that coming out, we keep randomly splitting the regions periodically in a same interval with the merging. And therefore, as a result of this, once the splitting and merging emerges, then the regions will represent the real access pattern of the given workload. And the number of the regions becomes same to the number of real different access patterns of the system and workloads. And further, we let users to specify the minimum and maximum number of the total regions of the monitoring so that users can control the minimum and maximum overhead. We are setting 10 and 1,000 as the minimum and maximum numbers as a default, and also recommending that. As a result, the visualization would look like this. And this means that the time overhead becomes the minimum of different access patterns, the real different access patterns of the workload, and the maximum number of the regions that you just set. That is, the overhead is no more ruled by the arbitrary memory size and fully controlled and auto-tuned because users can set the maximum number of regions, and the regions are automatically be as minimum as possible. And what about the accuracy? The accuracy will be best effort high because the auto-tuned dynamic granularity will allow DAMON to find very small regions of hot or cold memory area. And we still find more rooms to improve here because the definition of the region was not only about the space, but it was also about time. And from this example visualization, we show some inefficiencies in terms of time. There are multiple time-adjacent regions of similar hotness. These are also only waste, and therefore we optimize this by utilizing yet another counter that tracks how long the current hotness has kept. For this, we have yet another per region counter and count how many aggregation intervals, how many last aggregation intervals the current access frequency has kept. For example, as time goes by, if the access frequency is kept, then the counter is increased. If not, the counter is reset and then again counted from the beginning, like this. And therefore, we don't need to keep every snapshot to get the really interesting history, really useful history, but we can just discard every snapshot that already outdated. That's the snapshot is the visualization and the output of the DAMON. So the overhead becomes the only upper bounded by the maximum number of regions that the users can specify. So both time and space overhead are no more ruled by the memory size or total monitoring time that we cannot control but can be arbitrarily high. And the one more optimization is needed because there is an elephant in the room that I was just not mentioning about, and you might already realize that. That is, we described about the sampling interval and the aggregation interval. Those are, I was just mentioning that maybe we can just, you can just find the good values for sampling interval and aggregation intervals, but those are really important to get good monitoring research because when they are appropriate set, like this example, we can show meaningful enough information from the monitoring research. But if the intervals are too short, then as you can show, everything will just look cold. That is, there is no meaningful information that you can further use for optimizing your memory management of the systems because everything is cold and nothing can be distinguished. And in opposite way, if the intervals are too long, then everything looks hot like this. And this is, again, not useful for real optimization of the memory management because, again, everything looks hot and therefore nothing can be distinguished what is important or not. And also, if the sampling to aggregation interval ratio is too low, maybe this can be one idea that you can think about, that is setting the aggregation interval very long or sampling interval very short, then maybe it will be able to capture every access event, and therefore the monitoring research could be useful enough and accurate enough. However, in this case, most of the sampling would return only negative research, which means that unnecessary CPU cycle waste. That is, for each of the sampling intervals, you need to check the access, and it is also spending some of the time and CPU resource. And if it is always saying that, no, this was not accessed, then why you would waste the CPU cycles? And therefore, we have implemented an auto-tuning mechanism for setting the optimum sampling and aggregation intervals. For this, we are changed the questions from how to do, that is, in what time interval should we do this and that, to what you want to achieve, what amount of information you want to get from the monitoring research. That is, this mechanism lets users to specify desired amount of the access event to capture in each of the snapshots, how colorful the snapshot should be, and minimum and maximum sampling intervals, so the users can still set the minimum and maximum bounds of the interval so that the auto-tuning doesn't go too long way. And then the auto-tuning mechanism uses a feedback loop mechanism internally to find the optimum sampling and aggregation intervals by increasing both sampling and aggregation intervals if less than desired amount of events are captured in current snapshot, and vice versa, decreasing the intervals if more than desired amount of access events are currently captured in the current snapshot. But this may also raise you a question. So yeah, it's auto-tuning, but still it is introducing yet another parameter for auto-tuning of the parameters. So we are just increasing parameters, not reducing the parameters. However, we believe that at least the newly added parameters are easy to answer about. And also we have at least a default values that we believe that we can suggest, and something that we aim to continue supporting. So we are suggesting to set the 4% of the per snapshot theoretically possible maximum access event as a desired amount of access event for auto-tuning, and setting the minimum and maximum sampling intervals at 5 milliseconds and 10 seconds, and having the sampling to aggregation interval ratio at 20. So these are values that made as another heuristic, only just heuristics, but we have proved that these values work on some real workloads, and also we are aiming to support these values as a maintainer. So we have tested if this mechanism works as expected on real-world workloads, and we were able to find the auto-tuning is working and converging to optimum values depending on the load, amount of the load of the real workload. And also the resulting monitoring visualization was always something looks like, at least feels like, reasonable to make some distinguishment between different data of different access temperatures, like showing this. And the monitoring overhead was always low enough that it was about 0.0% single CPU time always. And the final one, the final part of the boring part, please. Cheers. So how we can then use this DAMON for access-aware memory management? There could be multiple ways. The first one is utilizing DAMON in profiling purpose. That is, you can just monitor the data access pattern using DAMON and visualize that and try to find some good findings from that, and that can motivate you. What can you do? Like, what is the real working set size? That based on that, maybe you can modify the given size of the memory of the system or doing some creative things. And also, you would be able to implement some kind of automated access-aware profiling research-based optimizations on user space or somewhere that is reading the monitoring research and then finding hot pages and then protecting those with some kind of MLOC system calls or using other ML-device system calls, like backing that with huge pages or no huge pages. And actually, we tried some of the tests with these approaches and was able to achieve about 2.3 times performance improvement on the very severe memory pressure situation, though that was just for test workload on very artificial setups. But why not just let kernels to just work? That if DAMON is inside kernel and most of the memory management actions can be executed inside the kernel, why not let DAMON to do that? So we have implemented another feature of DAMON called DAMOS, which stands for Data Access Monitoring-Based Operation Schemes. This is yet another phase of DAMON. So DAMON is not only for monitoring, but also access-aware memory management using this feature. This feature lets users to define access-aware memory management schemes that specify what are the interested access patterns of the users and what kind of memory operation actions the users want to apply to the regions of the interaction. For example, you could have interest in cold memory regions and you want to page out those cold regions, or you have interest in hot memory regions in specific NUMA node and you want to migrate those to specific different NUMA nodes. And DAMON is an execution engine of such schemes. And there are some more interesting details, but those should be out of scope of this talk due to out of time, so I will just keep that out of the talk. So that's the detail of the implementation of DAMON. And let me further introduce you a few more use cases of DAMON in real world. The first use case of DAMON is the proactive cold memory reclamation, as I just mentioned as an example usage of DAMON, finding cold pages and reclaim those as soon as possible so that we can reduce memory footprint without introducing degradation of the performance, like the AWS use case story was trying to do. And also this helps at reducing memory pressure occurrences and also can help capacity planning, because by running the proactive reclamation, the remaining real memory usage of the system or the mem used on the proc mem info could be real memory usage of the workload, and therefore you will be able to find real memory usage or working set size of the workload in very easy way when proactive reclamation is ongoing. And Amazon Aura Serverless V2 is using this DAMON feature for their memory auto-scaling service. And also there is another use case of memory tiering, that is when there are memory tiered systems that having slower NUMA nodes and faster NUMA nodes, then you can use DAMON to find hot pages and CXL NUMA nodes or slower NUMA nodes and then promote those to faster memory and vice versa. SK Hynix has developed and utilizing this for their heterogeneous memory SDK solution called HMSDK, and Mera has also implemented an improved version of that utilizing more self-tuning for memory tiering, and we showed about 7% performance improvement on test workload called TauBench. There are more ongoing works in this area for C-group fairness aware extensions, and also we are trying to extend DAMON to monitor not only access source CPU oblivious access, but also information containing the access originating CPUs, so that we can extend this for not only CXL-like memory tiering, but more general NUMA balancing use cases, supposing GPU or CPU attached NUMA nodes. And also there is one interesting approach to interleave memory for better memory bandwidth control that developed by Micron. They argue they have shown 25% performance improvement with this internal project. And also there could be interest in monitoring of the data access pattern for different types of pages, like what would be the access pattern for anonymous pages, file-backed pages, active RLU pages, pages in inactive RLU list, and for pages that unmapped or pages that backed by huge pages. For this kind of things, we in Meta has developed extensions of DAMON features for this usage, and we were able to break down the data access pattern of the systems for specific types of pages, like seen here. And also, we have recently worked on implementing DAMON features for more fleet-wide data access monitoring. That is, data access monitoring research of DAMON is showing where, when, how frequently the given memory was accessed. That is very good information, but some kind of too much information to aggregate on fleet-wide monitoring, and therefore we have invented another metrics called hotness distribution in name of idle time percentiles were called memory tails that's shown here as a visualization. And we have developed this for Mera for fleet-wide workload access pattern profiling, and was able to show the fleet-wide access patterns on some of our real workloads. And there could be any future opportunities. We are open to change DAMON for whatever users need. So we aim to just randomly evolve for user requests. So if you have anything you want, please make your voice. And finally, getting started. To get to start of using DAMON, you can just visit the DAMON project website, damonitor.github.io. It should contain everything you need to start using DAMON. If it is not, please yell on me or report generously. And the feature is available on Linux kernel starting from 5.15, though we recommend to use latest kernel as much as possible because there are new features that developed after the initial merge, and also please feel free to ask any help at backporting some of the DAMON patches on your kernels if you have to use all the kernels. And the features are also backported and enabled on major Linux distro kernels, and the DAMON user space tool, which is written in Python, is also available on major Linux distros, packages, systems. And there are multiple interfaces, and we always recommend you to start from using the DAMON user space tool because it is easiest to use, but you can also use more interfaces depending on your use case. If you are a kernel developer, maybe the DAMON kernel API should be the right interface for you, that is, use appropriate interface for your use case. And we have the community, we have mailing lists, we have bi-weekly virtual meetups, so if you have any questions or need help, or you have patches that you want to get reviewed, please feel free to send that. If you are not familiar with the mail-based development, we are developing a tool for such case named HKML, so please feel free to use that. And again, the future of DAMON is open for community, so please let us know. So the summary, the DAMON of today is that a Linux kernel subsystem for practical access monitoring based holistic and observable memory management, and currently being used in real world for a few use cases. And the future is always open and up to your voice. Please make your voice. So that's it. Any questions?
So it is your assertion that all these people that are posting patch sets to the mailing list, touting their new access method for migrating CXL memory back and forth between DRAM, that's not necessary because you've already done it and it's all in user space and it's wonderful and it works.
I'm sorry, I didn't get the last part of the question.
You've already done it, it's in user space and it works.
You're right. So, yeah, the implementation from SK Hynix is in user space, and yeah, it is working at least for their use case, and some of our the open source test workloads, that is, we have tested that against our benchmark called DCPulse, and one of the workloads in the benchmark suite called Tauband, and it was showing some improvements in some way. Yeah.
Okay, thank you.
Yes. Do you have any example of a specific case where DAMON struggles monitoring efficiently, or does it work always great?
Yeah, thanks for a nice question. So, yeah, actually there were so many such troubles and problem reports. That is, there were many cases that people were unable to find good monitoring research after following the tutorials of DAMON getting started guideline. Actually, there is one of the people who reported the bad research from the guideline. And in most cases, that was because of the wrongly set sampling and aggregation intervals. That is, there were a report saying that we tried that for monitoring the access pattern on the physical address space of our systems, and it was showing only some random things. And we nearly always found that those were because the sampling intervals and aggregation intervals were not set appropriately, and that was before the auto-tuning features for these intervals were developed, and that was the motivation of these auto-tuning features.
Thank you.
I have a question. So you mentioned a few slides before this one that you decided on a 4 millisecond sampling.
I'm sorry, can you please?
4 millisecond sampling that you discovered it works well.
40 seconds?
4 milliseconds, if I remember correctly. Anyway, you discovered a sampling rate that works well. And I was wondering why that. Nyquist's theorem tells us that if we sample, we need to sample 2 times the frequency of the signal. So what's happening? You know.
I'm sorry, I didn't get the question.
So I remember that. So one of the slides you mentioned that choosing a sampling rate, right? What happens? Like, is it 4 milliseconds or 4% or something like this?
Yes.
4%, yes. So, and then you mentioned sampling 1 to 20. Why these values?
So as I just mentioned, this is just a heuristic based on my gut feeling. So,
Sure.
Yeah. So I have resulted in the 4% because I was trying to apply the Pareto principles, and I was thinking that, so 20% of input result in 80% output, and if we apply that twice, 20% of 20% is 4%, and would result in 56% of output. I'm not sure if it is making sense at all. However, anyway, I was trying a few different numbers and resulted in finding that 4% was working pretty well on different workloads on real world. So I have resulted in, rather than finding more optimum values with more and more testing, more and more time-consuming testing, I just decided to let's set this as a default one, and let's stand there as a maintainer to support to users' use case. That is, I'm not saying that this should be something that never changeable or just optimum, but depending on users' use case and reporting, we will continue to discuss together at finding better ones or helping them at using this appropriately.
Thank you.
Anyone for 50 euros? Anyone? Thank you.
Thank you.